Right, here's the solutions to your physics exam from year 10. Different way of going through it means you can select which question you want. So ticks are valid points that you've made, not necessarily a mark on the mark scheme, but at least you're talking about the right thing. A dashed line would be, again, you've made some sort of physics correct statement, but it's not to do with the question, and a cross isn't. What you've said is actually incorrect. The numbers, if they're circled, are for subparts of the question, and then the numbers in the box at the end is for the total question. So it should be that the number in the circle should add up to the numbers in the box. So you get your equation sheet. Haven't done all of those yet, but it's just the full version. And on to the first question. So we're looking at non-renewable energy sources. So coal's given, so we've got to give another two. Gas, oil, pretty straightforward. You could have given nuclear as well, because it doesn't say, and I think I'll highlight this, they're the fossil fuels, okay, but nuclear is non-renewable but not a fossil. So funny graph, okay, all over the place, and that doesn't matter, just got to talk about the graph. So wind turbines do not generate electricity constantly. How many hours is there none? Look at the graph. How long is it before zero? And it goes from 2 o'clock or 1400 right up to 6 o'clock 1800. So that is a total of 4 hours. National Grid, again, shouldn't snuck this in really. It's part of next year, but it's fine. It's just cables and transformers, and it doesn't matter that you don't know what those things are. That's fine. And then Ireland has a large number of wind turbines. That's the kettle, if you can hear that. What am I doing? And large number, yeah, unpredictable. Okay, so that one is the most true. You could argue the toss on any of those, but that is the most true of all of those things. So we need to provide 1500 megawatts. Each one will give us 0.6 megawatts. So the number of anything, doesn't matter whether you're talking about wind turbines, whatever, is the total you need divided by what each one will supply. So it's 1500 megawatts divided by 0.6 megawatts, and that gives you 2,500 turbines. Final part of the question. Why is it important to get new ones? It's because of that negative environmental impact. They're bad. Right, circuits. The questions don't go in, they go in numerical order, but I took them from all over the place, so that's why this one's 3 and not 2, so that's fine. So DC current, that is always the same. Okay, first equation, question coming up. Equation's given. Okay, so that makes it slightly more straightforward. So always show your workings, okay, every single time. Doesn't matter how clever you are, you have to tell somebody else how clever you are. So that's just 0.4 times. Now this was quite hard actually as an initial question, because it's not just one resistor, it's two. So if you want the potential difference across the battery, you have to work out the potential difference across all the resistors. So because they're in series, we can just add them up into one resistor, which is the same as having 20 plus 10. Okay, so it's like a total resistance of 30 ohms. This question's got complicated quickly actually, but you seem to handle it pretty well, so I'm not going to labour the point. And if we throw the numbers, we throw the numbers in, we end up with, I don't know what I was doing there, 12 volts, okay? And then again, equation given, this one is ever so slightly harder, but I'll probably highlight that in a second. And it's because of the fact that we have the equation, so we calculate it through. That's easy. But then you've always got to check if you've got to do anything with your calculation answer. And in this case we do. We have to round it to one significant figure, and that's 5. Not 5.0, 5. Right, always got to check whether there's that extra layer of necessity there, okay? That's the easy bit, and then double check. Okay, really, really important to do that. Oh, yeah. Right, moving forward, temperature bomb. Okay, so first thing that it talks about is we've got a traditional thermometer that you've probably seen, and then a digital thermometer that you may or may not have seen. Okay. When I was reading through the data, I'm going to change time into seconds. Just get used to doing it, even if you don't need to. It's just it's good process. And we've got to talk about why student A's is better than student B's. Fine, okay, we can do that. It's definitely, you can't misread, it's harder to misread a digital meter, but the second one, or the second part to get, is about the resolution of the device. Okay, so the one on the left has a higher resolution. Now what resolution is the smallest division between 2 points. Okay, so a ruler, for instance, has a resolution of 1 millimetre. A stop clock has a resolution of 1/100th of a second. So if we had the one on the right, they're the minimum differences, 72, 73, 74, so the resolution is 1 degree C. The one on the left, we can go up in 0.1s. So therefore the resolution, or down, the resolution is up 0.1. And a higher resolution tends to, not always, tends to lead to better results. Don't try and stay away from, we need to drill into what the word accurate, reliability, or all that sort of stuff means. But for the time being, just a higher resolution is better. It's probably the easiest way to say it. So, if he took his, next bit of the question, so if he took the thermometer in and out every single time, lots of people, I suppose, systematic, but that's difficult because systematic has to be exactly the same every single time, the error. And I don't think it would be. I think you would take it in and out in a different way. So then if it's an error, repeated error that's different every time, that's random. Okay, but that's quite a difficult, subtle difference between them. So here's the cooling curve of stearic acid. I don't know whether you did this as a practical or not, but it's quite a common one, and one certainly we can redo if you feel there'd be value in that at some point next year. So it's showing it cooling, and that point there it's not cooling, it's changing state, and then it cools down again. Something cannot cool down and change state at the same time. Can't do it. Okay, which is why we get that flattening of the line. It's not nothing's happening, it's that it's not changing state. So the first question is talking about what's the temperature change. So read off the axes. That's 64. Again, I couldn't really see properly when I was doing this on a scanned version, but at 55.6, stole that from the mark scheme. So the change is 8.4. Be careful looking at axes and how many small squares there are and what the scaling is. They'll try and catch you out with that all the time, okay? Really important that you stay sharp with that. Don't know what I'm doing there. So, time taken for a solid to a liquid. So I've already touched on that it is, it's that flat line. That's where the change of state is taking place. We know that first point is 160. and we know that or we can read off that the later point is 900, so the difference is 740 seconds. You were allowed a little bit of leeway there, but not a huge amount. So 740 seconds. Okay, equation again. So get it from the data sheet. So there's some skill in picking the right one. Q equals ml. And then we have the mass. That number's given. And I think I needed to look the answer up because I couldn't do that in my head. It was about 79,000. And then I think I disappeared and found out what the actual answer was whilst just leaving it all running. A bit stupid really. Probably manically digging through pieces of paper. And yeah, 79,600. Randomly turn it off, put it back on again. Don't have to do anything to that number in terms of significance, so happy to move on. And then after 12 seconds, why does it go down? Loads of people wrote all sorts of silly stuff, but explain is quite difficult. You're not describing, you're not stating, you're not recalling, you're actually having to explain something. There's nothing there to help you. You've got to use your physical ideas. And we've got 2 marks, so we're looking for two separate points. Now, anything cools down, or its temperature goes down, if something hot is in something cold. Okay, always. Now, the initial temperature of the stearic acid at that, it says 1200 seconds actually, so I've got this slightly wrong, but hopefully you'll all forgive me. It's the same point, just with a different number. So after the time, I think I changed how I write this, but after the time, the acid is still hotter than the room. So if it's hotter than the room, heat will flow out of the hot thing into the cold thing. That's the only way heat can go hot to cold. That's how things are heated up or cooled down. If you think about putting it in a kettle, the metal bit's absolutely boiling hot, well, even stupid word, is really hot, about 800 degrees C, and then the water you put in is about 20. So you turn it on until the energy flows out of the hot thing into the cold thing, and it gets up to 100, and then a sensor flicks it off. So a really important point to make. So it's hotter than the room, so heat flows out until it's at room temperature. Obviously, acid doesn't have a sensor inside it, so that's the end of that. Right
now to see if it's recording.
Don't know what I'm doing now.
Audio.
Hopefully I am just waffling. Yeah. Yeah, I don't know what I was doing now. Oh, I'm talking about hot going to cold until they're both at the same temperature.
Right, first circuits question. And a practical, one of the required practicals out of 12 that you'll do over the course, minimum of 12, is looking at how we investigate current and voltage. So we draw our power supply, which is defined as 12 volts in the question. We've got our bulb, and our other component is our variable resistor. Now, if we left it like that, that's a fully operable circuit, but we couldn't take any measurements, so it's not a decent enough experimental procedure. We want the current, which we'd measure with an ammeter. We want the potential difference of voltage, which is in parallel. You've got to remember, ammeters are in series, they measure current, and voltmeters are in parallel, and they measure voltage. Posh name, PD. So again, how are we going to use that circuit to talk about resistance experimentally? Now you've got to remember, in physics you don't do anything once, you do a series and try and plot graphs. That's the key to describing any experiment. Normally there is a slightly different one. later in this test actually. So get a series of results and plot a graph. That's really what we're aiming for. So just to say get this, get that, doesn't work. So we'd measure current with the ammeter. Nothing wrong with writing in shorthand using I for current and the symbol for ammeter. No spag marks in this exam. So measure V with the voltmeter. Okay. Then vary the variable resistor. Measure new I and V. So what we've got to now, what we're getting towards now is an I and a V. Okay. Calculate R, because that's V over I. So that will allow you to populate that column if we were actually doing this as an experiment. And then plot anything you want. Well, not anything you want. Let's do, in fact no, let's not. No, let's do that. So plot, again you don't want to be describing what happens to R as I goes up or as V goes up, it's up to you. But whenever you're talking about this, what you're going to measure and with what. So even if it's something as simple as measure the length, say you're going to do it with a ruler, and repetition. Okay, so here's the student's results. Okay, describe how the resistance of the filament lamp changes as the current through it increases. So as I increases, R increases. Okay, now a few people put directly proportional. Definitely not, because directly proportional is straight line through the origin. Okay, 0, 0. That's not straight, and that's not an origin. So that's a very difficult statement to make about this one. So it's actually the rate is increasing. The gradient at this point here is about that, and the gradient up here is even higher, so at an increasing rate. Use figure 6 to estimate the resistance of the lamp when the current is 0.1. Now this caught loads of people out because you saw this said 0.8 and the next one is 0.9. Lots of you said that the next one then is 0.10. Now if I showed that to your maths teacher, they'd be angry, okay, because it's actually 1.0. Is it? Let me rub it out. There's 0.10. It doesn't say 0.10. It says 0.1. But look at it. Look at the two numbers. Too many people made silly error there. And all you had to do was, oh, pen's gone a bit. Oh god. Oh, that doesn't look good, does it? Program's disappeared. Back, hopefully. Okay. Follow that one back, and then read this value off the scale. So it's about 6.8 ohms, something like that. I've not got a decent enough scale there, so you can have a look at yours. But it definitely, numbers do definitely not go 0.9, 0.10, 0.11. You need shooting for that mistake. So be careful. You're better than that. Now you should have seen these graphs before. This one is a filament lamp or a bulb. This one is a resistor at constant temperature, and this one is a diode. You've done this experiment. I remember seeing you doing it, and you've plotted those graphs. They're in every textbook which is available to you online and every revision guide. So you've got to learn your stuff, okay? Really important.
Right, I've just wasted a bit of time being stupid, so I'm going to have to go back through these questions again, and hopefully it's a bit clearer. So, electrician with a shower, replacing it out. Why has he got to switch off the mains? Again, 2 points. Could get electrocuted, and lots of people got that, but you've got to be able to say which part of the cabling would do that to him, and that would be the live wire. Equation, so you're given the equation here, so you've got to throw the numbers at it. Again, you get a bit of a funny number when you do that. Again, you can check your calculations relative to mine, but then there is this necessity again to check what you've got to do. I've got to make it 2 significant figures, so I have, and then I'll pop that answer in there. Okay. Again, you can pause the video if you need to. Shower has a new higher power rating. Okay, so it doesn't work. So that would make it more expensive, and more power means more energy in the same time. Okay, so if you had a 5-minute shower, then it would use more energy in a higher power, because energy is power times time. I think that's in the next question. This number goes up and this one stays the same, then that number goes up. That is what costs. Okay. So gases, okay, the point I was trying to make previously before I had to redo this was you've got describe. Okay, so just say what you see. So what we've got, we just compared to, let's just say that's one and that's another. Those arrows represent the speed. The longer they are, the faster it is. So what we've got is a range of speeds. Don't make a comment on fast or slow because you don't know the temperature. And they're in a random direction. Okay, and clustered together, that could be called Brownian motion. What's kinetic and potential energy called? Well, it's definitely not called, that's why I scribbled it out. Definitely not called movement energy. Okay, so it can't be that one. So if you ever get a multiple choice, narrow your options. Okay, so is it internal or external energy? Well, hopefully internal energy makes more sense. But that's good technique. Get rid of the one that it definitely can't be, or other options if there are other options. Okay, and then slim your guesses down if you need to. I did this with this group. Okay, so we talked about the equation, density. Remember, we used this. That's not density. Okay, symbol wise. Okay, it's this. If that was a line, this was the letter A. That was letter B. That's density. Okay, row, and you plug the numbers in, and you get the answer. Okay, nothing to do in terms of checking. Again, pause if you need to stop and think or ask. National grid, so we talked about that earlier, it's just all the cables that are all around the world. I suggest one reason why it's between 3 and 6 on a Monday, because that's people getting home, so they start to use the electricity. Again, when I just went through this, one time, don't give a range of times, it asks for one. I gave you the mark, but do as it says, so anywhere between here and here really. Somebody went to 5 o'clock, but that's sort of about there. Okay, it started to go up by then, so there are better answers than 5 o'clock. Why do we limit our use of fossil fuels? It's so we can reserve them, okay, and so it doesn't over pollute. I'm going to have to read. So, sun heats the water only by 0.6, that's a tiny amount. What's the resolution? So we talked about resolution a little bit already. If this was our 0.5 one, we'd get a reading there, and then that would be it. We wouldn't be able to take another reading. If we have a higher resolution, get a reading there, reading there, reading there, reading there. That is better, more readings. Okay. Get rid of that. So 0.1. Oh God, right, so what I've done. So what I did as I went through this section here, okay, so that section, is as I was reading it, I was circling the important information. So I know that that's the amount of energy, which thermally we call Q. You could just call it E. Oh. Okay, makes no difference. There's your change in temperature. Time, 300 seconds. Okay, I made the conversion of this number straight away. There's specific heat capacity. I've just gone through and plugged the numbers in. Okay, so power is energy over time. And then I did the calculation with specific heat. Now what I'm trying to do over here, or what I did do over here, and I had to redo it, is just to say, is that this is how they make equations harder. Give it, just use it, remember it, that's harder, and then remember and rearrange, that's even harder. Now, although you're not asked to remember this one because it's given on the physics equation sheet, rearranging people struggle with, okay? And that would be the harder aspect of the question. Explain why that's only mean power, and that's because the sun would give different. If here's my pot, the sun there, the sun there, the sun there would give different amounts of energy or power to the object. All right, I've caught up now, that's good.